Hello, friends, and welcome to Live from NOIRLab at Tucson, Arizona, home of Kitt Peak National Observatory. I'm your host, Rob Sparks, with our moderator today, Jamika Marshall, and our guest today is Knut Olsen of NOIRLab here in Tucson. He's going to be spinning us a tale of two galaxies and of how they interact with each other. I'm really looking forward to this one. Remember, if you have any questions or comments, you can enter them in the chat box, and Jamika will relay them to our guest, Knut. Oh, come on now. My slides don't want to advance here. There we go. First, I'd like to tell you a little about Kitt Peak. Kitt Peak is funded by the National Science Foundation and is a NOIRLab facility. It was founded in 1958 and is located on about 55 miles southwest of Tucson on land leased from the Tohono Nation. We are indebted to them for letting us use one of their sacred mountains for astronomical research. Kitt Peak is home to over 24 optical telescopes and 2 radio telescopes. Before we begin, I'd like to highlight a recent image of the week from NOIRLab. You can find our image of the week on our website, noirlab.edu. This one was titled Stairway to the Stars. It shows the iconic McMath Pierce Solar Telescope. This solar telescope happens to be polar aligned. So if you put a camera at the base of the telescope, it goes straight up to the North Star. This time photo, literally hundreds of photos layered afterwards to show the rotation of the stars throughout the night, shows that. You can see at the tip, the North Star rotating just about a very small circle around the tip of the McMath Pierce Solar Telescope. This telescope is no longer used for active research. However, it is being refurbished for the Windows on the Universe Astronomy Outreach Center, which we hope will be opening after in the post-COVID era. Next, I'd like to introduce our guest, Dr. Knut Olsen, is a staff astronomer and the CSDC Community Science Data Center Principal Data Scientist at NSF's NOIRLab. He started work on Magellanic Clouds through his PhD thesis with Dr. Paul Hodge at the University of Washington, and he continued exploration of them while living and working in La Serena, Chile. He now lives and works in Tucson, Arizona. And at this point, and I'd like to say that most of what I know about tidal streams, I've learned from Knut. So I'd like to bring on Knut this time. He can turn on his video and webcam, and I will turn over to him and his presentation. Welcome, Knut.
Hi, thanks. Great to be here.
Yes. So take it away. You can share your screen, and I'll mute out here for you.
Okay, let's see. Here we go. So can you see that?
Looks good.
Okay. There we go. Great. Yeah. Thanks for having me on to talk about the Magellanic Clouds. So this image that you see here on the title slide was taken by Anja von der Linden. It's a beautiful photograph from the top of Cerro Tololo Inter-American Observatory. And you can see the band of the Milky Way going across. This is a panorama shot. You can see the telescopes of Cerro Tololo, including the 4-meter with its silver dome there. And then off to the left of the 4-meter, you see what look like 2 little clouds almost. It's the large Magellanic Cloud and the small Magellanic Cloud. These are, naked eye objects from the southern hemisphere. We call them the Magellanic Clouds, but cultures living in the southern hemisphere have, of course, incorporated them into their cultures, and they have many different names. The name that has stuck for professional astronomers was the one that was given to it basically by Europeans, named after Ferdinand Magellan, who circumnavigated the globe. But they have many other names as well. And this is, so I'm obviously not the first person to have studied the Magellanic Clouds. They've been studied for many hundreds of years, and as I said, other cultures have been observing these for millennia. What made them special to me was I had finished my thesis on the Magellanic Clouds using Hubble Space Telescope data in 1998, but I'd never actually seen them with my own eyes. And so when I got a postdoc job down at Tarantula, I was able to see them for the first time with my own vision. And so in the decades that followed, I've worked on the Magellanic Clouds in various ways. And so what I'm going to talk about here is sort of a personal journey studying the Magellanic Clouds that were introduced to me by my thesis advisor, Paul Hodge. He passed away last year. And so I sort of dedicate this talk and things I've written about it to him. Yeah, so it's a personal story about science, about the Magellanic Clouds. Hopefully it'll be interesting, and I'm happy to take questions. So just some brief background on the Magellanic Clouds. There's basically a new data set focused on the Magellanic Clouds. So this is that picture of the small cloud is a composite of lots of dark energy camera pictures stacked on top of each other. I'll talk about that a little bit later. But the Magellanic Clouds are two of the nearest galaxies to our own at distances of 160,000 and 200,000 light years. The large Magellanic Cloud is a little bit closer to us. You can see them as galaxies in detail, but because they're also outside of our Milky Way, you can approximate the stars within them to be at a uniform distance, which makes it them very useful for astronomy, because when you're looking through the Milky Way, you're often looking, it's like seeing the forest for the trees. With Magellanic Clouds, you get a panoptic view of them, and that has translated into them being used as laboratories for lots of astrophysical processes. There's more than 15,000 papers related to the clouds, of which my thesis added 2. So there you go. Within the large Magellanic Cloud, you can there's lots of interesting things to look at. That box here that I just highlighted is I'll go to next. So this is the biggest stellar nursery in the local group, in our local group of galaxies. This is called, I would ask people if anyone knows the name of this, but it's called the Tarantula Nebula. In the Northern Hemisphere, it's not all that familiar because we can't see it from our Northern Hemisphere location. But it is forming stars at a really prodigious rate, and is the most massive star-forming region in the local group of galaxies. A more familiar star-forming region is the Great Nebula in Orion, shown here. That's in our Milky Way galaxy, and it's at a much closer distance. It's also a massive star-forming region, but it's really dwarfed by the Tarantula Nebula, or 30 Doradus, as astronomers usually call it. And so I wanted to put these two on the same physical scale. So if you were to move the Orion Nebula to the distance of the Tarantula Nebula, you would get this. And so you see the Great Nebula in Orion as this tiny little postage stamp up in the left corner of this image, and is dwarfed by the Tarantula Nebula. So if the Tarantula Nebula were at the distance of Orion, it would cast shadows at night. It would cover something like 1/5 of the sky, and it would be just a beautiful object in the night sky, and quite domineering, I think, of our view of the sky. So it's absolutely huge. At the center of this nebula is a star cluster called R136. It's a massive cluster of very young stars. And I wanted to, so where I'm going to jump into the story is that as this massive cluster of stars can tell you a lot about how stars form, especially massive stars, and how they evolve. I was working with people who were interested in understanding the stellar evolution of massive stars, and so I wanted to give you an idea of the kinds of things we were looking for. So here is a simulation of a massive star cluster when it has just formed. So on the right is an image that I've made up, right? So this is not a real image, but it approximates that of R136. And on the left is an HR diagram where I'm showing temperature on a plot on one axis of this plot and luminosity on the other. And I'm going to play a movie that shows what happens to both the star cluster image and the Hertzsprung-Russell diagram. So this is an HR diagram as time goes on. And what you'll notice is that very quickly, right? So the time is going up here in billions of years. Very quickly, those bright blue massive stars evolve away and die, and you're left with fainter and more luminous stars. And as you're looking at this, it looks like the stars are zipping around on the screen. They're actually in the simulation totally fixed. And what you're seeing is just the very short stages of stellar evolution that stars go through towards the end of their lives, and they get much brighter and redder, meaning that they're cooler. And understanding those fast stages, those late stages of stellar evolution is very important for understanding how stars are built and how they evolve. And so that's what we were doing. We're actually looking for, here I'm going to show a Hertzsprung-Russell diagram again. So the temperature, which is increasing to the left, and luminosity, which is increasing up. We were studying these late stages of stellar evolution, red supergiants. And this has been a career for Phil Massey, who is pictured down here in the lower right-hand corner. For me, I was just getting into it, this was a project that Phil had going that he was going to use the Hydra CTIO spectrograph. It's a multi-object spectrograph that I was the instrument scientist for. But his observing run was interrupted by the tragedy of 9/11. He wasn't able to fly because a lot of planes were grounded. So I joined to help out on the project. I was living in Chile at the time. I only had to drive up to the mountain to take the data. I collected the data and worked with Phil, and so we'll see what came of it. One of the things that came out of this study was Phil had an undergraduate student at the time, Emily Levesque, who modeled the spectra of the stars that we observed, and got a really nice result as an undergraduate, where she adjusted the temperature scale such that these stars agreed well with stellar evolution models at the time. There had been some discrepancy. And in the process, was able to conclude that these red supergiants are some of the largest stars around. And this became a story that was picked up in the news. And just to give you a sense of perspective here, here is an image of the sun with the planets laid out on the table. And below is another perspective where a red supergiant, VY Canis Majoris, is shown next to the sun. And the sun is absolutely dwarfed by this giant red supergiant. So these stars have radii thousands, something like 1,000 times the radius of the sun. Emily is now an astronomer. She's a professor at the University of Washington, and has actually written a book called The Last Stargazers. the story of her discovery is featured in that book, along with many other really great stories from astronomy. So I recommend that book. Phil and Emily recently, you might have heard about the star Betelgeuse in the news. It's a red supergiant as well. And sometime last year, it started to dim quite a bit more than people had seen in a long time. And there was a lot of speculation about whether it was going to blow up as a supernova. I think somewhat hopeful, but Phil and Emily were able to show that this dimming that happened with Betelgeuse was actually due to a cloud of dust that had been likely belched out by the red supergiant. So we know that red supergiants are great places to form interstellar dust. And this happened to be an episode where lots of dust had been formed and shadowed the star and made it appear dim. And its Betelgeuse has started brightening again to normal magnitudes. So that was a really cool result that followed up with the work they did that I was just describing. The thing that I was interested in with these red supergiants was to try to use them as tracers for understanding the dynamics of the Large Magellanic Cloud galaxy. And here I'm showing on the left in this multicolor picture, which you can ignore the colors for now. But each of these points is a red supergiant for which we got a spectrum. And which means that we got observations that showed how much light there was at individual wavelengths of light. And it's laid on top of an image of neutral hydrogen gas, which comes from a different telescope altogether, a radio telescope. But what we would do is red supergiants, because they're so cool, they have lots of, and so big, they have lots of spectral lines in them that are quite narrow and are really great for measuring line of sight velocities from the Doppler shift. So basically what we would do is we would take an observed spectrum, like this black thing, and overlay it with a template spectrum, a star for which we know the line of sight velocity, and we would slide it back and forth until they matched like this. And that would tell us the velocity, because we know that if something is moving towards us or away from us, it shifts the wavelengths of light which that object emits through the Doppler shift. And so you get a measure of the velocity of a star. You don't get the full 3D motion. You only get the component of the velocity projected into your line of sight. That's important. But you can use that information to deduce how fast the stars in a galaxy are spinning. And so we did this. So these red points are the red supergiant data, overlaid with velocities of the neutral hydrogen gas, which I'll talk about a little bit later. But you can see that the red supergiant velocities, they rise and they flatten out. It's called a flat rotation curve, is quite typical of galaxies, and is a useful thing to know because this was the kind of data that Vera Rubin originally used to discover dark matter, right? So she in the 1970s, she made observations of the rotation curves of galaxies, just like we were doing, and found that in galaxies, she would trace the velocities of the stars in them. And so her points here are these yellow dots, but you can also see how much light there is from the galaxy. And if that light is if the matter is emitting light, then you expect the velocities to decrease as you go further out, just like the velocities of the planets in our solar system get much lower the further out you go. But instead, what was she was seeing was that the velocities would be flat or sometimes increasing, which meant that there had to be some matter that wasn't traced by the light that was increasing the pull of gravity to the point where it would cause the velocities, the orbital velocities, to increase. So this was the discovery of dark matter, and it has stood up to the test of time. We think it's 25% of all mass in the universe, but we still don't know what it is. It's one of the great mysteries of astronomy. Anyway, that's a digression, but dark matter was important. And this is sort of a digression in the story that I was just telling about red supergiants. Because since we don't know what dark matter is, we'd really like to know, try to find some. And so I was working with a group of astronomers led by Armin Rest, pictured here in the bottom right-hand corner, to basically use the Large Magellanic Cloud as a probe for dark matter candidates. So one of the ideas at the time was that dark matter might be these massive compact objects in the halo of our galaxy, so outside our galaxy, in between the Large Magellanic Cloud and our galaxy. You should be able to find some of this if it existed. And the experiment was to basically monitor every other night fields in the Large Magellanic Cloud, and they're these squares are the fields that we were looking at, and with the hope that one of these machos, the massive compact halo objects, would cross right in front of a star in the LMC, the Large Magellanic Cloud, and by doing so, cause, through gravitational microlensing, cause that star to brighten. And as time went on, it would brighten and then come to a peak and then decrease again. So by measuring events like that, we could hope to try to detect some of these dark matter candidates. Of course, there are many other things in the LMC that vary. So a little bit about the procedure that we were using here. You basically take an image, and this is an image taken from October 2001. Lots of stars in it in the Large Magellanic Cloud, and some nebulosity. That's there's also lots of that in the Large Magellanic Cloud. And we would take another image a little bit later and subtract the two and look for things that changed. And so in December, we took another image of the same field and subtracted the two. So basically everything that's bright here in this picture is emitted more light in December than it did in October, and everything that's black was brighter in October, and everything that's gray is basically the same brightness. So most of this image is gray. You can see a few bright things here. So these, are the kinds of things that you'd be looking to monitor to see if they behave like microlensing, which might be dark matter. But the most striking thing in this particular picture, of course, are these weird rings, which caught us really by surprise when we found them. So we took another picture of the same field in 2002 and subtracted them again. You can see the rings have grown a lot more prominent. They're bigger. And again in 2003. And you can calculate the rate at which these rings are expanding. You can see that they're seem to be growing bigger. That expansion is occurring at the speed of light if the rings are at the distance of the LMC. We were not the first to have discovered this particular event, but it was surprising at the time when we saw it. And you have to ask yourself, what's at the center of the rings? Well, at the center of the rings is a supernova explosion, supernova 1987A. It had blown up in 1987. It was a really well-studied supernova because the LMC is so close. It kicked off a lot of work on supernova. It eventually led to using supernovae as distance indicators, which then led to the discovery of dark energy. But that's an entirely different digression. But anyway, we were observing this light in 2004, and the supernova had blown up in 1987, right? So what was happening was that what we were seeing was echoes of that supernova light. So basically, when we get light from a supernova, the first light that we see is the one that has taken the straightest path to us. But the light can also take other paths. If it happens to bounce off something like dust and the Large Magellanic Cloud, it'll take a longer path to get to us. In fact, these path lengths here for some of these rings meant that it was taking 15 to 20 years later to observe that same original light from the supernova that we had seen before. In 1987, I was a teenager, more interested in playing electric guitar than in astronomy. And so I hadn't seen the supernova, but now we can actually go back and study supernova like this, even after the explosion. And so this is just an explanation of why you see rings. Basically, these sheets of dust are cutting across ellipsoids of equal time travel time. So if light from the supernova bounces off a sheet of dust here and comes to us, it'll get there later than the first light. And if you have a sheet of dust, there's actually a ring on the sky that has the same light travel time. And so that's why you see these rings, and those concentric rings are then sheets of dust at different distances from the supernova. And looks like there might be a question on that. No? Okay. Yes, there is a question.
Just a comment here. So just want to welcome everyone in our YouTube audience. I am joining you here from Mauna Kea at the Visit Information Station, which is closed to the public, but I am outside. There is no one here, but I'm outside testing Wi-Fi stability for a future program. And here, I am very excited to be able to moderate from here for both of you all. So our comments, we have a few people in the audience from Arizona who have been to Kitt Peak and wanted to say hello and that it's amazing and fantastic. We also have people who have seen the Large and Small Magellanic Clouds and just wanted to share that with you.
Excellent.
And as you were talking about the supernovae and the light curves, are the light curves expected from all supernovae now?
Mm-hmm. Yeah. In fact, so I'm going to talk about that next, right? So we had found these this light echoes from supernova in 1987A, but as we looked at other images, there were supernova 1987A is this circle here with the light echoes, and these arrows are showing, the locations of the light echoes and their direction and apparent velocity of travel. But we found lots of light echoes that had nothing to do with supernova 1987A. So if you take these arrows where you see the apparently moving nebular ghosts, they point back to different locations. And these other light echoes, they point back to supernova remnants from type 1A supernovae, which are much more massive explosions. It's a different kind of mechanism that causes the star to explode and produces a much brighter supernova. But these had occurred hundreds of years ago, right? So what Armin is doing now for much of his research is to look for these echoes from historical supernovae that could be hundreds of or thousands of years in the past, and actually studying the original light from the supernova by taking spectra of them, by mapping the distribution of different pieces in those spectra, doing really great research by using light echoes as a tool to peer into the past. So it's a great question. So this was a digression. I'm just going to quickly get back to my main line of work at the time was on the dynamics of the Large Magellanic Cloud. And as I mentioned, we were finding this flat rotation curve for the red supergiants, but you can see that the gas, there are some of the gas, that neutral hydrogen gas has a flat rotation curve, but a lot of it does not. So this part in particular does not follow this green rotation curve that I've laid out. And something one should know about the Large Magellanic Cloud and the Magellanic Cloud system is that if you look at them in radio wavelengths, so if you had radio vision and you took an all sky image, you would see something like this. This is an image actually from infrared light of the Milky Way disk, right? So that's the bulge of the Milky Way. And you see dust obscuring part of our vision. And then here in red is radio data from neutral hydrogen gas taken by David Nidover of the Magellanic Clouds. And you can see the Large Magellanic Cloud here, the Small Magellanic Cloud here, but the most prominent thing is this stream of gas that connects and flows out from the two and actually goes ahead of them. And we think this stream of gas was actually pulled out by the interaction of these two galaxies around each other. And so if you look at what these arms here are, they are arms that come off the Large Magellanic Cloud and actually connect to the Small Magellanic Cloud and the Magellanic Stream. And so these are arms that are somehow tied up in that interaction. And this was important because if we, after collecting data on the red supergiants, we collected velocities of lots of stars, not just red supergiants, but older ones as well. And we got this map of velocity on the sky, and you can see we can transform this map into a rotation curve. And so here's that same flat rotation curve from the red supergiants, and lots of these older stars are following that. That's these green points. But these blue and red points are stars that fall way off that rotation curve, and most of them happen to lie on what we think are these streamers of gas that were involved in the interaction between the Large and Small Magellanic Clouds. And this was puzzling, right? Because I'm going to just take a minute or so to look at this figure, right? So when you have a spinning galaxy disk and we're measuring the velocity of stars along the line of sight with the Doppler effect. And that disk is spinning and it's tilted to you. So the Large Magellanic Cloud disk is a little further away on this side than it is on here. What you see as it rotates is that on this side, the stars will appear to approach you. And so you get blue shifted velocities. And on this side, they're moving away. And so you'll get red shifted velocities. And when it's moving across your line of sight, you basically get no Doppler shift at all. But what we found for these stars that fell off that flat rotation curve is that those stars had the opposite velocity gradient compared to the normal stars. So these stars look like they're spinning this way, clockwise. And these you might interpret as spinning the other way, right? I mean, it's like finding a planet in our solar system that was going the opposite way from everything else. But the trick is that because we only measure the motion along the line of sight, we don't know for sure that these are in the same tilted plane as the rest of the LMC disk. They could be in a different tilted plane, actually spinning in the same sense, but it would appear as if this side was moving away and this side towards you. And so to resolve that, right? We found these stars with strange velocities. We also found some star clusters with strange velocities. And our interpretation here, which I'll get to, is that these stars were actually pulled out of the small Magellanic Cloud in their interaction. But so why is this geometry ambiguous? Well, so as I just explained, I mean, you get this velocity gradient, blue on one side, red on the other, as the disk is spinning. But if these stars that look to be spinning in the counterclockwise direction were actually in a plane that was highly tilted with respect to the LMC plane, you could get them spinning in the same sense, but they would just be very far out of the plane, something like 55 degrees. And this would agree with an interpretation where those stars are part of the debris that has been pulled out in this interaction between the Magellanic Clouds. And we can use new data to resolve this ambiguity. So this is from the Gaia satellite, which has observed very precise positions of stars and tracked them over time. And you can actually see basically on the sky, the stars of the Large Magellanic Cloud spinning around. And over here, I've taken those stars, most of the LMC stars, Large Magellanic Cloud stars, are spinning this way. And those things that look to be counter-rotating also happen to be spinning in the same sense. So now we think we have a complete picture that there are some stars, something like 5%, that are in a plane that is not in the same plane as the bulk of the disk. And it's connected with these arms that we think are being pulled in, and those from the small Magellanic Cloud falling onto the Large Magellanic Cloud. And those arms focus on 30 Doradus, the star forming region that I talked about at the start. And so we think this interaction, and what we found evidence for, is that these arms, that interaction, is essentially providing the pressure, pressing down on 30 Doradus very, very with high pressure, so that all of the massive star formation in it can keep going. Because if there was no external pressure, the supernovae and the stellar winds from those massive stars would blow the cloud apart. So we think this is what's keeping it together and making it such a massive star forming region. And how that interaction might have happened. So here is a simulation from a collaborator, Gertina Besla, where she has modeled the small Magellanic Cloud and Large Magellanic Cloud over time. And in her model, about 300 million years ago, the two galaxies actually collided directly. And so we think what we might be seeing is the evidence of that direct collision of those galaxies. So here is that model with all the stars in it, and here is just from the small Magellanic Cloud. And right here, you see these stars from the small Magellanic Cloud right on top of, stripped out by the Large Magellanic Cloud. And this could actually explain what we had thought was gravitational microlensing in the LMC, that other thing that I talked about. Because rather than having dark matter now, what you have is a lot of debris around the LMC, and it's not such a great system actually for trying to find dark matter candidates. We're looking now even wider around the LMC. So this is from Gaia, showing that interaction has produced tails of stars here. And we're actually finding that stars from the LMC, this is an HR diagram of the LMC, and this is a little stub. It's actually going out to like 20 degrees. So that's 40 times the diameter of the full moon. So these stars are all over the sky, pretty much, and tracing exactly how far they go and what the debris looks like is a really interesting question that we're studying. We think this interaction has left behind warps. So this is a study from Yumi Choi using that SMASH data where she measured distances along the line of sight and found this bend. here in the LMC, and probably has left rings. So this might be a feature from that we see from this interaction. Might be the signature of that collision. Finally, we know that the Magellanic Clouds, they're a satellite system to the Milky Way, and as they're coming into the Milky Way, we think maybe for the first time their orbit is being bent by the Milky Way, but they're also, because they're so massive, they're actually pulling on the Milky Way itself. So our Milky Way galaxy is responding to the mass of the Large Magellanic Cloud in particular. And this data is showing that measurement shows that at some distance you see stars coming at us essentially. So the Magellanic Clouds are hugely important. We've thought of them traditionally as satellites of the Milky Way. Turns out they may have their own satellite system. This is from a study of the Dark Energy Survey, showing satellite candidates, some of them perhaps satellites of the Magellanic Clouds. So the more data we get and the more deeper we look, the more interesting the story of these galaxies becomes. I wanted to leave you with maybe a vision into our future, where we can use astronomical data to see into the past. We can also try to predict what's going to happen in the future. And this is from a study by Gertina Bessla and her collaborators and others, looking at the motion of the Andromeda Galaxy. So this is a picture that it's a simulation, but it's something that you might see if you went to a really dark site now. So here is the Andromeda Galaxy. But now that we can measure the motions of these galaxies, and we have some idea of what galaxy collisions does to star formation and the structure of galaxies. So if we were alive 2 billion years from now, Andromeda Galaxy will look something like this on the sky, and because it's coming towards us at several hundred kilometers a second. If we were alive 3 3/4 billion years from now, it's getting very close. And then just shy of 4 billion years, the Milky Way and Andromeda will appear to collide. And in that process, all this pressure from gas will cause that gas to form stars, just as they're doing in 30 Doradus, and light up. And so the night sky will be a totally different view from what we have. And if we were around to see it, you would see fireworks like this. Eventually, the two galaxies would pass through each other, and so you'd see Andromeda on the way out. And eventually, something like 7 billion years from now, they'll merge into one galaxy. All of the gas will have been used up, no more stars forming, but the night sky will be bright with stars. I'm not planning on living that long. So, just to leave you with some conclusions, these are some of the things I talked about. I won't belabor these points. I think the main point is that as I worked on the Magellanic Clouds, we can find ways that they're connected to almost every sort of important astronomical discovery in some way. And we don't know everything about them. And I think the main point that I really like to make is that scientific research is a story. We don't know the ending of it, but you can always jump in and learn something new and play a part in that story. I've written up a lot of this, what I presented in this talk, in this Astronomy Magazine article that's just out now, and I think you can access it on the web. So if you want to learn more, you can go to that article. And that's all I had. So thank you. Should I stop sharing?
Yeah, you can stop sharing now if you like. And if someone has a question, ask you to go back to a specific slide, you could start sharing again. But okay. I will just that Astronomy Magazine article, you're right, it is on the web. And either yesterday or the day before, we shared it on the NOIRLab social media channels. So if you want to find it, you can go there, or you can go to the Astronomy Magazine website.
Yes, and actually we will have it in the video description once this is posted as well.
Ah, great. Excellent.
I do have a few more comments and questions, if that's okay.
Sure.
All right. So first, we have joined us in the chat from La Serena is Leonardo Paredes, and he said that the large and small Magellanic Clouds are some of his favorite sites.
Yeah. I know Leonardo.
Oh, okay, good. And so actually we're talking about the largest small Magellanic Clouds and the simulation of how things go, potentially what it could show us in the future. What's the margin of error on these kinds of simulations, and how can you quantify what you can actually get from it and say, yeah, this is dependable data?
Yeah, so that's an excellent question, right? Because the simulating the collision of two galaxies is really complex, and depends on what you think you know about the mass of those galaxies, how that mass is distributed, their motions through space with respect to each other, and the timeline. And there are many parameters to look at. I would say that what Gertina Besla found when she modeled these is that given our data, the sort of, you get families of models that will look different in detail, but have some of the same features, like whether there was a very close passage or not, or whether the Magellanic Clouds are on a bound orbit and have orbited the Milky Way many times, or whether they're coming in for the first time. And the models that are favored are the ones that have a massive LMC, more massive than we had previously thought, that are coming in for the first time or have maybe made one or two passes around the Milky Way. And that the SMC and the LMC must have had some kind of recent close passage to kick out all this debris. And so it's, if a simulation is very rarely going to give you an exact match to reality, because there are too many things that go into providing those kinds of details. But broad questions like, how many orbits have they made? Have they come very close to each other in the last few 100 million years? Are things that you can say with some certainty, but of course there's always going to be that chance that there's something that you've ignored in the model, and that changes everything. And so that's kind of the story of science, that you can get what you think happened with pretty good certainty with the data that you have, but then you've made a wrong assumption, or you get some entirely new data or a new view of things, and that changes the picture completely.
Thank you for that. And, also you mentioned that, of course, I think most of us who are familiar with the large and small Magellanic Clouds do know of them as satellite galaxies, captured galaxies. But you're saying that this new data suggests that maybe they have, their own things orbiting them. Tell us about that. Was that unexpected?
Yeah. So this was a result that came out when Nitya Calabayolo and her group, they were able to measure the transverse motion, so the proper motion of the large and small Magellanic Clouds. And those were basically, those measurements showed that it was very hard for the Magellanic Clouds to really be captured over long periods of time around the Milky Way, that they were likely coming in for the first time, or maybe had made one passage. Well, I think it's likely that the clouds are bound to the galaxy. They're bound in an orbit that has a very long period, so it's a highly radial orbit. That are, depending on the parameters, you can also make them unbound so that they're coming through, and then we'll keep going on the way out. But yeah, that was a total surprise because when you see two galaxies that close in the sky, your sort of tacit assumption is that, oh yeah, these have been around the Milky Way for forever, when that's likely not the case.
Yeah, that caught my eye too. Those things around the Magellanic Clouds pretty neat. Anything else in the chat, Jamaica?
Oops, sorry. Yes, actually, we do have a comment and question from Leonardo. So Leonardo says, yes, this is great talk and awesome new things happening on the Magellanic Clouds. And he has a question. What is the science that you're looking forward to seeing on the Magellanic Clouds with the Vera Rubin telescope and DESI, for example?
Yeah, that's a great question. So the kinds of things that we like to do with the Vera Rubin telescope, right? So Rubin will get really deep data, and we'll also get many epics of data. So a movie of the sky, and with those we can not only map the full extent of the structure of the Magellanic Clouds, basically all over the sky. And we'll also be able to use tracers like variable stars for which you can get pretty good distances to actually get a 3D map of the Magellanic Clouds. And I think that will really give us a much more complete picture of the clouds and their past history, their interaction, how they're put together. And I think will teach us likely surprising new things about them and other galaxies, right? Because when it was a surprise, for instance, to discover that these satellite galaxies probably have satellites of their own. These really faint dwarf galaxies are really good places to look for dark matter because there are so few stars compared to basically this lump of dark matter that we think are in them, that if you want to study dark matter, that's probably the place to go. And every time we've sort of gotten more, sort of much more data on the Magellanic Clouds than we had before, something has come up that has kind of come out of left field. And so while it's not guaranteed to happen, I'm kind of expecting us to discover something with data like from Rubin that we just don't even know to ask yet. With DESI, it could certainly have an impact. So it's in the northern hemisphere. There are stars from the Magellanic Clouds that you can see in the north. But I think we'll certainly also want to follow that up with spectroscopy from the southern hemisphere, because that's where you get much more visibility of the Magellanic Clouds.
Thank you so much. This is I really appreciate your explanation because it's clear enough for me. So hopefully it is for everyone in the audience. Okay, and with just 5 minutes left, let me share the last comment and question from the chat, and then I will be back to you, Rob. So our question is on the kinematics of the Magellanic Clouds. It says, you showed that those kinematics are taken from red giants. So considering that M dwarfs are made up of 75% of the stars, makes up 75% of the stars, is it possible that those unseen stars could have different kinematics?
So it is possible, though, right? So the M dwarfs, you can see them really deep observations of the Magellanic Clouds, but it's really hard to get spectra of them. So we don't have spectra of M dwarfs in the Magellanic Clouds, but we do know that we can look at the star formation history, which we can measure from stars of lots of different types, including the oldest almost unevolved stars. And so we can look at these as populations, and those red giant stars that we're using. So the red supergiants, of course, are young, so they could certainly have quite different kinematics from M dwarfs, most of which will be a lot older. So the stars that we were looking at in the sort of second stage of our study, which were the older evolved red giant and asymptotic giant branch stars, have ages more similar to the bulk of the M dwarfs. And so as long as we can use age of the stars as some indication of the population that they come from, they can get a decent handle that we would we could predict what the M dwarf kinematics would be like. It would be something like that of the older population, not like the red supergiants. But it's if we were able to get spectra of M dwarfs, that would be great, because then there would be so many stars that we could get velocities of. And then you could look for really subtle things like kinematic subpopulations, and even things that you just can't see with a more limited data set. So yeah, great question.
Okay, well, thank you very much, Knut. We're
Mm-hmm.
pretty much approaching the end of our hour here. So thank you for joining us and giving us a fascinating look at the Magellanic Clouds. I love seeing them for my first time when I got to Chile back about 7 8 years ago as well. That was just a magical moment.
Mm-hmm.
And Jamaica, I believe next week is live from NOIRLab at Gemini, correct?
Correct. Live from NOIRLab at Hawaii, and we will be on our regular time Wednesday, 2 p.m. HST, 5 p.m. MST. We look forward to look forward to all of you joining us right here on the NOIRLab YouTube channel.
All right.
Thank
Okay.
you. And that will back to Wednesday next week, since we're out of the holiday week. So I hope all you have a great holiday at home, and you too, Knut and Jamaica. And we'll
Happy
see
Thanksgiving.
everyone